Hi everyone, and welcome to our deep learning road trip for physicists. Buckle up, because over the next few minutes we will explore how neural networks help us squeeze knowledge out of every kind of physics data you can imagine. First things first, let us look at the incredible variety of data that pops up in research. On screen you will see classic data flavors. The upper left panel shows a sensor amplitude marching forward in time. The upper right panel is a telescope snapshot, an image grid filled with light intensity. Lower left is a so-called Lego plot from a particle collision, where each tower's height marks energy deposited in a detector cell. And finally, the lower right panel is a rapid-fire sequence of pulses, tiny blips that arrive one after another. No matter the flavor, our first job is to package these numbers into suitable portions as input to the network. Concept number one is putting all numbers into a single input vector we will simply call x. That works for a time series with regular time intervals, as in the upper left figure. As network input, we can thus use the entire vector x. Alternatively, we could also input a first subset of vector x, let the network work with that, and then input the next subset of vector x. Concept 2, regular grid data. In the camera image of the upper right panel, each pixel's value sits on a neat two-dimensional hexagonal lattice. Also, the lower left figure exhibits a regular grid using the two variables eta and phi. Both can be viewed as a matrix. We could input the entire matrix into the network, thereby concatenating row after row into a long vector. Alternatively, we input a submatrix only, let the network work on it, and then input the next submatrix until every piece has been digested. A simple form of a matrix are event-based data tables. Picture a spreadsheet where every row holds one event and every column a different measurement. Row after row, column after column, we end up with k events and n variables, easy to feed into a network. Extend the input to irregular grid sequences, as in the lower right figure. Stack a whole film reel of images together, and you've got a video. Each frame is a regular grid. The timeline links them into a sequence. Input image by image into the network, or if your compute memory allows, the whole video. What do you do with irregular patterns? Imagine sprinkling measurement points through three-dimensional space temperature points in a room, or particle hits in a detector. Each point carries its own position vector and the value you assign to the individual point. Altogether, we call a point cloud. And what about heterogeneous sensor ensembles? Maybe you run hundreds of seismometers, GPS antennas, and pressure gauges all at once. They are wildly different, yet together they paint a single picture of the underlying physics. So far, we have talked about data. But what about models? Traditionally, we would bake in physics laws right from the start. Let us see how that works. Here is a classic. We know an earthquake sends waves racing outwards. We have 4 sensors in red and quite a number of earthquakes in that region marked as black circles. Each earthquake sends 2 types of waves, namely compression waves and shear waves, which expand with different velocities shown in purple and green. Being physicists, we consider their time of arrivals at several stations and triangulate the epicenter using the well-known wave velocities. That is our physics-driven modeling. No neural network is required. Now let's contrast physics-driven versus data-driven model building. Instead of writing down a formula, we can let a neural network discover the hidden rulebook purely from data. In a data-driven model, we would train the network using a set of established earthquake data with their arrival times and the corresponding epicenter. The network would digest the times of the 4 sensors for the first earthquake, namely the raw arrival time of the compression wave and the arrival time of the shear wave. For simplicity, we show here only 4 of the inputs. On output, the network should predict the latitude x and longitude y for the quake. Initially, this prediction will be off. However, showing the true epicenter to the network, it will adjust its network parameters for more precise predictions. After enough training, we evaluate the network's quality. For any brand new data of the arrival times at the sensors, a well-trained network will give proper predictions on the earthquake epicenter. To make the contrast crystal clear, we never handed a physics formula to the network such as time equals distance divided by velocity to the network. The network is not required to have a bachelor in physics. It simply learns from the data given to it. The network itself becomes the model to describe the earthquake data. Now let's look at a simple, more abstract example in one dimension, only to watch the network adapting its parameters during training. The top panel shows a bunch of black data points dotting x values and their function f of x values. Before training, the network draws a crazy squiggle nowhere near the points. But watch what happens after a few hundred learning cycles, called epochs. The network prediction curve improves in describing the data points. Why should the network improve? We give it the so-called objective function, also known as the loss function. The objective function tells the network how far it is from the points. A common choice is the mean square error, which measures the distance between the points and the predicted curve. This information about the residuals is used to improve the network parameters. Finally, the red curve hugs the points quite beautifully. In the lower panel, the objective function drops with the training epochs, a proof that the network parameters converge. So, the path to successful model building turns out to be a minimization problem, just as we know from fitting data. And that, friends, wraps up our grand tour. We started with data in every flavor, cruised through model building mindsets, and landed in the land of well-trained networks. Thanks for joining us. We will see you next time on our deep learning journey for physicists. Until then, have fun and stay curious.